Hello there. We're starting a new unit today, and this one is a bit of a doozy. We are going to talk about nuclear and quantum physics. Now, it's important to recognize that the topics that we cover in this unit, we're really just kind of scratch the surface of each of them. So you'll probably be left with a lot of questions because we're just giving it a quick overview of each of these topics, and these are very, very big topics and often very confusing ones. This is going to be just our brief overview of these. So starting with nuclear physics and this idea of fundamental forces. So we talk about in our universe, we have fundamental forces that cause things to behave in certain ways, for planets to orbit suns and things like that. And so to understand these, we're going to dive into what's happening on a nuclear level when we zoom into atoms. So the nuclei are composed of two nucleons known as neutrons, which is given the symbol N0, and protons. And that's probably something that is not brand new news to you. The number of protons that you have in an atom is called the atomic number, and it is going to dictate what kind of atom that is. So if you have one proton, no matter what else is going on, then that is definitely hydrogen. And if you have 6 protons, no matter what else is going on, then that is definitely carbon, whatever else might happen. Now, the number of protons and neutrons added together is the mass number. So if we add up the protons and the neutrons, they add up to the mass number, and we give that the symbol A. Now, for any given element, you can have different numbers of neutrons, right? So carbon is always going to be 6 protons, but it might have 6 neutrons, or it might have 8 neutrons. And that's going to, even though that keeps the element the same, that's going to change the mass number. So elements with different numbers of protons are called isotopes. And they're going to have the same number of protons, but different numbers of neutrons. So when we do this shorthand, we use this nuclear notation you see over here on the side. The X here in this is just the chemical symbol. Okay, so H for hydrogen and so on. A is our mass number, and Z is our atomic number. So if, for example, you wanted to talk about uranium 235, you could just abbreviate that as U for uranium. 235 is the mass number, and uranium always has 92 protons in it. Okay, so we know about atoms. This is not brand new news to us. But now we're going to dive into this idea of the fundamental particles. And it's going to bring something called the standard model of particle physics. So fundamental particles are particles that have no smaller parts. And that's as simple a definition as I can think of. Basically, once upon a time, we thought maybe everything's made of these little tiny things called atoms, and it turns out we were right. But when we looked closer at those atoms, we found that the atoms are made of smaller things. And as we started to look at those smaller things, even some of those are made of smaller things. But as far as we know, when you boil it down, there are certain fundamental particles that are not made of anything smaller. That's as small as it is. They are their own discrete things that exist on that scale. So an example of fundamental particles would be things like quarks. Quarks are fundamental particles, and leptons are also fundamental particles. And if those sound like made-up words, they kind of are actually, but they're our physics words now. Now, these all fit into something that you see over here called the standard model of elementary particles. So basically, the standard model, it just shows all the fundamental particles as we currently understand them. Now, when you first look at this standard model, it can be a little bit overwhelming. It is, however, organized in such a way to kind of help you understand a little bit about these particles. Now, you do not need to memorize this. I'm just going to point out a few kind of key highlights about this chart that you hopefully will understand. Now, we talked about fundamental particles like quarks, okay? So quarks are a fundamental particle. In fact, the two maybe most common ones that you might run into in your day-to-day life are going to be up and down quarks. As it turns out, up and down quarks is actually all we need to make regular run-of-the-mill protons and neutrons. So they are both made of quarks. Now, let's see how this works. A proton, it turns out, is made of 2 up quarks and one down quark. Now I know it's a little small to see, but if you look in the corner here, an up quark has a charge of plus 2/3. And you might be wondering, how do you get fractional charges? Well, just bear with me for now. So both of these have a charge of plus 2/3. A down quark, as it turns out, has an overall charge of negative 1/3. Now 2/3 plus 2/3 minus 1/3 gives me an overall charge of plus 1. And that's what we know about protons. They have an overall charge of plus 1. With neutrons, let's take a look at that. The up quark is positive 2/3. And each down quark is minus 1/3. Well, 2/3 minus 1/3 minus 1/3 is an overall charge of 0. And that's what we know about neutrons. So protons and neutrons are made of these smaller fundamental particles called quarks. And they're held together by something called a gluon. Now over here on this column here, you'll see we've got our bosons. And they are basically force carriers. So they are the particles that mediate the different forces that we know about. Things like the strong nuclear force or electromagnetism. Now again, try not to get too complicated. You can see that there are other versions of quarks. There's charm and strange and top and bottom. Now the difference with these quarks is that they differ in their mass and therefore their energy levels. So you can make a regular proton out of just up and down quarks, no problem. But it turns out that in some special situations, really high energy interactions like in particle colliders or in stars, we can have these other particles exist, these higher mass, higher energy quarks. Now, if you look just below the quarks, you'll see there's a collection of things called leptons. And one of those will be very familiar to you, and that is our good friend, the electron. So it turns out that even though protons and neutrons are not fundamental particles because they're made of quarks, electrons are. Electrons aren't made of anything smaller. Now, just like with quarks, you've got your regular run-of-the-mill electron, but you can also have situations, high energy situations, that have larger mass, higher energy versions of the electron, such as the muon or the tau. And again, these are going to exist in specialized situations. Regular everyday matter only needs your up and down quarks, plus your electrons, and away you go. On that bottom row there, you'll see we've got neutrinos. Now, each of the leptons is paired with a neutrino, and we're going to talk about those a little bit later. But for now, just recognize what's going on with the charges and the masses. So electrons, we know, have an overall charge of -1. But if you look at all of the neutrinos have 0 charge. And I know that the units for the masses on these are really, really weird. Like they're measured in mega electron volts per speed of light squared. And we'll get to that. But just recognize that compared to the size of the electron, for example, the neutrinos are very, 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 very small. So they're these tiny, small mass, no charge particles. Okay, so let's think about how this all comes together in an atom. Now we know that atoms come in all different varieties, and they're all different based on their internal structures. So we've got neutral atoms. The number of protons is just equal to the number of electrons, because those are the only charged constituents of the atom. Now, the electrons make the atoms really interesting. So the number and arrangement of electrons are going to give the atoms different properties, like what other types of atoms they want to react with and what kinds of proportions. It's going to change things like their atomic spectra or whether or not they're magnetic. We use Bohr diagrams to kind of represent our atoms in a very simplified way. Now, even Bohr knew that these diagrams were not what atoms actually look like, but what they do really well is they help us understand just the general idea that we've got a central nucleus that is positive. It contains our protons and our neutrons, and then around the outside that, we've got our electrons. Now, not just anywhere though. The key insight with the Bohr diagram is that the electrons exist at really specific energy levels. So what Bohr is trying to show here with this diagram is that the electrons can exist in these different orbits, and they're at very specific levels. The closer the electrons are to the nucleus, the lower energy they are, because that's where electrons want to be. They want to be close to the nucleus. And the higher up or the further away from the nucleus they are, the higher the energy level they're sitting at, because they they don't want to be far away from the nucleus. So this brings us to our 4 fundamental forces. And what we say is that our current understanding of physics, there are 4 forces that kind of mediate the behavior of particles that are in it, okay? So the first one you're quite familiar with is gravity. Now, gravity has a long range, and we know this because, for example, Earth is being affected by the sun that's very far away, but then our sun is affected by other things in our galaxy, and galaxies interact across huge distances. But the thing about gravity is that it is very, very weak. It takes a lot of matter to generate a significant amount of gravity. By comparison, electromagnetism also has a long range, but it is much stronger. For example, the reason you don't fall through the seat you're sitting in is because the electrons in the seat and the electrons in you repel each other with a very strong interaction. Now that brings us to weak nuclear force. Now, weak nuclear force is kind of a strange one in that it only really shows up or becomes important in something called certain types of radioactive decay involving neutrinos. And if that sounds like I'm just kind of waving my hands in the air and saying physicsy stuff, I kind of am. It's a complicated process, but for now, just understand that as far as we know, it needs to exist, and it really just helps explain how certain types of radioactive decay happen, and we'll explore that more in a later video. That brings us to strong nuclear force. Now, strong nuclear force is by far the strongest. It's not just a great name, but the thing about the strong nuclear force is that it only works over a very short range. So the strong nuclear force drops off quite dramatically with larger range. And it is responsible for holding the nucleus together. So if you haven't thought about this before, you should have some questions about how a nucleus works, right? Because we spend all this time talking about how protons are positive and they repel other protons with this really strong electromagnetic repulsion, and yet we're okay with the idea that all of our atoms have these protons jammed together in these really tight small spaces we call a nucleus. And the reason for that is the strong nuclear force. So nucleons, like protons and neutrons, are attracted to each other by the strong nuclear force. And it is very strong, but it can only work over very short ranges. So, for example, if I try and put 2 protons together, 2 hydrogen nuclei together to make a helium, they're going to try and repel. But if I can get them close enough that the strong force actually kicks in, then they'll actually fuse together to create a new nucleus. And again, that's something we're going to talk about in the future when we talk about fusion and fission and what's going on there. So as long as you understand that the strong nuclear force is very strong, but drops off dramatically with distance, then that's all you need to know about that for now. Okay, that is it for our first lesson on nuclear physics.